Very good. So in case you don't remember, we are learning conformal field theory. This is the second week of the course, and I'm Pedro. Okay? Very good. So I will start from the very basics, and in particular, what I'm going to start by is there is a big overlap with what Jaume said, but I just want to set up the notation and make sure everyone is on board with the notation and everything is clear. But you can do two things. You can either speed me up, which is fine, and I will speed up in the very beginning, because as I said, it will be mostly repetition of stuff that Jaume said for the first half an hour or so. Or, if you find it too basic, you can solve this exercise that I prepared here, which is kind of a warm-up, and it will be indeed relevant for maybe tomorrow, maybe after tomorrow, we'll start using this. So I just want to make sure that everyone will know a priori how to solve this. Here is what is called a Casimir, a conformal Casimir. It is a combination of generators of the conformal group. You saw all these letters in the previous week. And the claim is that it commutes with the generators of the conformal group. And then I'm asking you to tell me what is the action of the Casimir on conformal primaries, and for simplicity on scalars. Very good. So starting from the basics. So as Jaume started his lectures, CFTs can be thought of as the endpoints of RG flows, either the starting points or the endpoints. So if we have some theory that has some high energy or UV behavior, and then as we zoom out or go to low energies, we go to some IR description. And both in the UV and in the IR, there are no scales. Okay? And this is trivial why there are no scales, right? So if you are at if you take your system and go to very, very, very high energies, why is there no scale? Because you are at such high energies that all the masses of your particles are totally irrelevant. All your particles are moving at the speed of light, and they are effectively massless. So all the energy scales, if they exist, they are so small compared to the energy you are probing that you couldn't care less. So by definition, there is no scale when you go to very high energy. What about going to very low energy? Again, by definition, there is no scale. Because if you go to very low energy, the massive modes are simply not excited. You consider some low energy dynamics, and your energy dynamics is low energy by definition, so it doesn't excite the massive modes. So again, if you have some massive degrees of freedom in your theory, as you study large distances, they die off and you just don't see them. So both at very low energies or at very high energies, we have no scale. Okay? This is just by definition of zooming out and zooming in. Now, conformal symmetry is a little bit more than scale invariance, which is the absence of scale. Conformal symmetry is the statement that we have scale invariance at a local level. That is, that we can change our scale, you can zoom in and out, by different amounts in different regions of space. And this is a natural symmetry. If you imagine you have some magnet, and you zoom in a piece of magnet, and you find some scale invariance, some beautiful critical phenomena, you would expect that different pieces of the magnet that are far away don't care if you zoom in by different amounts, so you should have some sort of local symmetry. And it is not surprising if I tell you that actually most examples that people know of scale invariant theories are actually a bit more than scale invariant. They are conformal invariant. And although there is no rigorous proof, there are several attempts at proving that indeed the endpoints of RG flows are not only scale invariant, but are conformal field theories. Okay? So again, just to make sure everyone is clear, let's do a very simple example. What could be an non-trivial quantum field theory which has some scale? Imagine you have two free scalars, one which is massless and one which is massive. So let's take here two scalars, one massive, free scalars, one massive, one massless. What is the UV for this example? Two massless scalars. If you are at very, very high energy, who cares that one of the scalars is massive or not? Both seem massless from you. So you start from two massless scalars. And the IR, someone else. What is the IR? One massless scalar. Because now, if you are at very low energies, you simply don't excite the other massless scalar. Okay? So we start with a CFT of two free bosons, and we go to a CFT of one free boson. This will be, if you want, the simplest possible example. Okay? So what then is the definition of a conformal field theory? The definition of a conformal field theory, if you want, of a conformal field theory. It's an Euclidean quantum field theory with the property that the generating functional has the following property, that the generating functional of all your correlation functions in some given background G and J is equal to the generating function of all your correlation functions when you do a wild transformation on your space-time, on your metric, and you transform the current with the appropriate power, where, let me just define the usual function, as usual, e to the w, as John may defined it, is equal to integrating over all your fields, e to the minus the action in some given background of your field, plus the integral of your current times your field O, where here, for simplicity, I'm assuming this O to be a scalar primary of dimension that. Okay? So this definition of a conformal field theory is a theory where if you know how to put the theory in a given background, you know how to do local dilatations by any local omega square that depends on where you are in space-time. In particular, this definition implies that correlation functions of your theory, O1 at the point x1, On at the point xn, in a space-time which is omega square g, in a wild transformed space-time, is equal to omega at the point x1 to the power minus delta 1, omega to the minus delta n at the point xn, times the correlation function of our operators in the space-time prior to doing this local scale or wild transformation. Okay? So this is an implication. Is it okay? So I want to emphasize something that is important, that people always get confused about where do you put the wild factor, with what sign you put the wild factor, active versus passive. It's just a big mess. And I want to emphasize that it's always very important to work out some simple examples to make sure everything is okay, and to make sure that you put the minus signs instead of the plus signs, and that you have all the signs correct, and that you have all the dimensions right. And I want to emphasize a little bit this, so I will consider a very simple example. And a subcase of this general treatment of changing space-times by doing a local transformation is what are called conformal transformations. This is less general than what I just said, which are transformations where x goes to some new x mu, x tilde mu, such that the new metric is a wild transformed version of the previous metric. Okay? And I want to consider an example, just to make sure we understand well what we are doing and don't start applying too many conformal transformations. Let's consider inversion, where x tilde mu is just x mu over x squared. Then you can indeed check that dx tilde mu differs from the original dx mu by a wild transformation, by a wild factor, and this inversion factor of x is nothing but 1 over x squared for inversion. Okay? And now let's check that everything works out and that we know exactly what we are doing when we manipulate these conformal transformations. Let's start with the correlation function of a scalar in flat space. Okay? this is our object that we want to check that everything is consistent with what we are writing here. What is this object? It's the simplest possible thing. It is just 1 over x minus y to the power 2 delta, where delta is the dimension of this operator. Okay? And now let's apply everything that we wrote here in this definition. Hopefully everything will come out okay. Now let's consider the correlation function of the same operator, the same x and y, where now I do a local dilatation of my metric, where I change my metric by 1 over x squared dx mu dx mu. So I compute the same correlation function in a while transformed spacetime. Okay? Is it okay? So let's follow the rule. According to the rule that I said there, I should put the while factor to the power of minus the dimension. So the while factor is this, to the power minus the dimension. So I get x squared. This is 1 over the while factor to the power delta 1. Y squared, or to the power delta. Y squared to the power delta. Both deltas are the same. Right? Times the correlation function O of x, O of y in flat space. In the space dx mu, dx mu. In other words, this is just equal to x squared to the delta, y squared to the delta, over x minus y to the power 2 delta. This was just the correlator that we had in the beginning, which is nothing but 1 over the following vector, x mu over x squared minus y mu over y squared to the power 2 delta, which is nothing but the correlator of the operator at the point x mu over x squared and another operator at the point y mu over y squared in flat space. Okay? So let's think a little bit about what we have done and about how obvious it is, so that no one comes with confusions about where do you put the tildes and where you don't put the tildes, which is the most annoying thing. So let's see what do we have. What we are saying is the following. We are saying that we start, let this be the unit circle, the unit sphere. And we are starting with a point x here and the point y here. Okay? And then we are relating this configuration to what? We are saying the following. We are saying that we can either keep the points where they are, right? Keep the points where they are, but change the metric g to omega squared times g. Change the way you measure distances and keep the points where they are. Or leave the metric as it is. G continues to be g. But apply an inversion and map these 2 points to some points inside the sphere. Okay? And these 2 points of view are totally equivalent, of course. You can either change your scale or keep the space-time but change the points. But you better not do both. Right? Doing both is the same as doing nothing. It's like saying 100 euros is $140. That's nothing. It is just changing the number but changing the scale at the same time. You are doing nothing. You are not relating different things. You are doing nothing. So don't start doing conformal transformations and then changing the metric and then doing everything. Either you apply a local dilatation of space-time, fixing the points, or you change the position of your points, and this is equivalent because a conformal transformation has the net effect of a while transformation. Okay? So in general, what this relation here implies for conformal transformations, which, as I said, is a subcase of this more general identity that follows from a definition of a CFT, is that correlation functions, let's light it carefully once and for all, at point x1 tilde, on at point x and tilde, Okay, and now this will be an equation where both spacetimes will be in Rd, is related to the same thing where now I have the points prior to transformation, also in Rd, right? And then the factors here come with some weights like this. Okay? So this is a particular case of this, and it follows from knowing that a Weyl transformation is equivalent to doing a conformal transformation. The net effect of a conformal transformation is the same as not moving the points but changing your metric. Is it clear? Great. Now, having said this, I wanted to introduce this in this great generality of defining the conformal field theory in this way, because this allows us to do more interesting things, like the things that Jaume was briefly starting to touch upon in the end of his last lecture. Okay? So before, let me just put these equations in boxes. These are really the fundamental equations. Let me just add a box here. And this, which is a sub-case of the previous one, but often very useful, let's put it also inside the box. Now let's consider a different example where we do change space-time and where we go from flat space to a cylinder. Okay? So let's do something fun. Let's consider our space-time. So we start with d dimensions, which is just dr squared plus r squared d omega squared in the d minus 1 dimensional sphere. Okay? And we write this. If you introduce the variable r equal e to the tau, then this is nothing but there will be a omega square of tau that you can immediately tell me what it is, times d tau squared plus d omega s d minus 1. What is this omega of tau? Someone that didn't reply yet. What is omega of tau? So if you do this change variable, r equal e to the tau, you plug it here, what do you get here? E to the 2 tau, right? So this omega of tau is equal to e to the tau. Good. And what is this metric here? What is this metric here? It's a flat r plus a sphere times a sphere. So this is the metric of time times a sphere. R times a sphere. So this is nothing but omega square of tau times ds square of r times sphere. In other words, this is flat space. Let's draw a plane. And this space-time there, it's a cylinder. So it's time that goes up. And for each fixed time, I drew here a circle. But in general, you should think that each circle is a d-dimensional sphere. Just in the blackboard, I can only draw a circle. Okay? So this is tau. Whereas here, this is r, which is e to the tau. So fixing a circle here, right, is fixing a circle here. Right? Is it clear? Now let's see that things work out as we expect. And this is an example that I like very much to make sure. This is the example I always use to make sure that I have my signs right in the deltas, and you will see why. So let's see if this works well. Let's consider a point here, parameterized by some tau1 and some vector n1 that tells me in which direction I'm pointing and with what magnitude. And some point 2 parameterized by some tau2 and some unit vector n2. Okay? And in this picture here in the cylinder, one of these points is here at some tau1, and the other point is here at some later time, tau2, and they are pointing a priori in different directions. Okay? n1 and n2. Okay? And now let's compute the correlation function of these 2 points on the cylinder using what we know here. So what do we know? We know that the correlation function of my operator with parameterized by tau 1 and 1 with my other operator parameterized by tau 2 and 2 in flat space Rd is equal to, so let's use this definition, omega of the first point, so e to the tau 1 to the power minus delta, omega at the second point, e to the tau 2 to the power minus delta, times the correlation function of my operator, parameterized by tau 1 and 1, operator tau 2 and 2 on the cylinder. You agree? Is it clear? It's just using the box formula. And now we plug what we know for this value. So what is this thing here? This is 1 over e to the tau 1 and 1. This is the first point, minus e to the tau 2 and 2. This is the second value, and this is to the power 2 delta. Right? I multiply these exponentials to the other side, and I massage it a little bit, and we conclude that this expectation here is equal to, let me write the result, and then together we look at it and see that it's obvious, to 1 over cosh of tau 1 minus tau 2, 2 cosh plus 2 and 1 dot n2 to the power delta. Okay? So it's more or less clear what is happening here, right? So I'm just writing the square of this vector to the power delta. The square of this vector, it's this dot this, and this square, and then I'm putting these exponentials on the other side, massaging a little bit, and I get to this point, right? I'm not going to do the algebra. There's no point, right? But you see here something very important, that it is because of these factors and because of this particular sign that here it only depends on the difference delta tau. And this is, of course, what you expect. You expect that the correlation function on the cylinder has time translation invariant and only cares about this separation here, delta tau. So if ever you forget the sign of these omega transformations, you go and you work out this cylinder map and you figure out that the sign is such that the result has time translation invariance as it should. Yeah? Are you good? Okay, very good. And what else can we say about this result? Does it look reasonable? Well, it does look very reasonable because you see that this result behaves as e to the minus delta times tau 1 minus tau 2 for tau 1 much bigger than tau 2, which is exactly what we expect. We have these operators. Each operator was mapped to a state, as John explained at the end of yesterday, with energy delta, and as we stretch them, you just decay with the energy delta times the time of propagation. And if now you were to do a weak rotation, and why would you do a weak rotation? If you wanted to have really time times a sphere, and not time times a sphere where time is not time, their time is a space direction, but you rotate t to I tau, this would become the usual e to the I energy times t1 minus t2, which is exactly the factor that you expect for propagation with some energy that is just delta for some time t1 minus t2. Okay? Cool. So what are the consequences of conformal symmetry? So here I just wanted to display a little bit some known facts about conformal symmetry. I would like to discuss now a little bit of consequences of conformal symmetry. Okay. In the meantime, did someone finish the exercise? No? Not yet? Okay. But please don't forget to do it for tomorrow. So should I do this? This seems too boring. For example, the correlation function of two scalar operators. Is there any point in reviewing that? Or that's too simple? Should I review why the correlation function of two operators is fixed by conformal symmetry? Or should I skip that? Skip that. So let me give you but let me, however, say a few words that provide a derivation that is much faster than any derivation. And the derivation goes as follows, an alternative derivation. Step 1, you say that the result is unique. Why is the result unique? Because by a conformal transformation, you can map any points to 2 points that you want, 0 and 1. So suppose you map your points to 0 and 1. And now you want to know the correlation function at any 2 points. But that's trivial. Just use a conformal transformation and map 0, 1 to any other points. Find the corresponding factors omega and read off what the correlation function gives by mapping 0, 1 to whatever you want. Right? So the result is unique because any points x1 and x2 are equivalent to 0, 1. And therefore, all we have to do is start with 0, 1. Start with 0, 1. Prefine the conformal transformation that maps to x1 and x2. It comes with the associated omega of x. And the correlation function is given by just putting here 0 and 1. This is just a number. And you work out what the omega factors give you. And this is the result of the correlation function. So it's clear that the result is unique. But you don't need to do the computation. Because once you know that it is unique, you just write down the result and check. Because since you know it is unique, there's no point in deriving. Checking is as good as it gets. So now, the second step, I just tell you the result. OI of x, OJ of y is equal to, I can always choose a base where they are orthogonal, delta x minus y over twice the dimension of delta I. And really, I mean, you are laughing, but this is a proof. We proved uniqueness, and I gave you a result that obeys the right properties, so we are good. Right? And this is particularly interesting because now we can right away go to 3-point functions. And for 3-point functions, the result is also unique. Because if you have 3 points, x1, x2, x3, are always equivalent to 3 random points, say 0, 1, 2, or 0, 1, infinity. People like 0, 1, infinity, I don't know why. So we have 3 points, so we can always put 3 points at 0, 1, 2, apply a conformal transformation that maps you to x1, x2, x3, your favorite points, read off the corresponding omegas, and that will be the result of the 3-point function. So whatever it is unique. So again, I just tell you what the result is, and it's just a question of checking that it works. And the result for 3 scalars is O1 of x, O2 of y, O3 of z is equal to 1 to x minus y to the power delta 1 plus delta 2 minus delta 3, x minus z to the power delta 1 plus delta 3 minus delta 2. I'm still downstairs, I'm sorry, it's a bit messy. X minus y to the power delta 2 plus delta 3 minus delta 1. And if this guy is normalized to 1, this is physical now, and this is what is called the structure constants. Okay? And the simplest thing that you can do is to check. Everything is trivial to check. I mean, dilatations, you just make a dilatation and so on. The only part is special conformal. But you are not going to check special conformal. You check inversion because you know that special conformal is just an iteration of inversion, permutation, translation, and inversion again. So all you need to know is that under inversion, x minus y, the vector, goes to x minus y over x squared y squared. So under inversion, this is how it transforms. So all those weights pull out factors of x squared and y squared to a given power. And those factors are the factors that you need, like there, y squared, x squared, y squared, some powers that you need to make sure that you check the formula in the box. Okay? So once you check that pulling out these factors here give precisely the right powers of omega, you prove that 3-point functions are what they are because, as we said, they are unique. Good? Finally, I want to just write down, I don't want to spend time proving it because it's kind of algebraic and because we are going to rederive it tomorrow or after tomorrow. I want to tell you a little bit what if the operators have spin. Right now they were scalars. Up to now, what if they have spin? Okay, and again, Jaume also did it, but I know he did this a bit fast, so let me do it a little bit slower. So suppose we have an operator O S that has spin. So this operator OS that has spin, it's an operator O, which has some indices, mu1 up to mu L at some point of space-time X. And this is a totally symmetric tensor, symmetric traceless actually. Okay? So there is a very convenient way of keeping track of symmetric traceless tensors, which is you can dot this object with some null vector n. It's an auxiliary vector just to remove the indices, n mu1 and mu L. Then you have an operator without indices that has the same information as a symmetric traceless tensor. Then the correlation functions of operators with spin L. So I will always alternate between L and S because actually, I don't know, it's psychological. I cannot stick to one. So please correct me if I write S's instead of L's. An operator OL at some position X and OL at some position Y. It's also fixed by symmetry, and it is given by n dot x minus y to the power 2L over x minus y to the power 2 delta plus 2L. Okay, this is just. And if you have a correlation function of O of x, O of y, two scalars, and a third operator that is an operator with spin, this result is equal to, there are a bunch of powers, like for the scalar. I'm not going to write. You can work them out if you want. But the interesting part is the matrix. It's the tensor part because this is a tensor. And the tensor part is again some structure to the power L, but now the structure is a bit different. Is n dot x minus z over x minus z square minus n dot y minus z over y minus z square.
Sorry, can you say again? So what do we call a null vector?
It's a vector such that and mu is equal to 0.
So you would Minkowski signature now.
If it's not Minkowskian, I can do it in Euclidean as well. Imagine you have the vector, complex vector. I squared it minus 1.
I think that you said that OL is operator with spin, didn't you?
Yeah, that's right. So I'm considering operator with spin. A single label L parameterizes the representation, and I'm considering symmetric traceless representations of the conformal group of OD. Okay? It is just that symmetric traceless representations are the convenient representations if you want to. Well, it's not totally clear why I'm considering these representations at this point, but that's a statement. I'm considering symmetric traceless representations. The reason is that they are the representations that will appear when we'll be studying the fusion of scalar operators. So if you are considering a physical process where your external points are scalar operators, actually in the intermediate process, these are the only representations you can generate by group theory, which is a non-trivial statement, and we'll come back to this later. But for now, I'm just telling this. O is a symmetric traceless tensor. And if O is a totally symmetric traceless tensor, a useful way of dealing with this tensor is in contracting it with a null vector.
Just I'm confused because not every operator with spin can be generated like this.
No, an operator with spin is this. Now I can do whatever I want with this operator. Definitely I can contract it with a vector. Why not?
So it is not the most general spin operator.
It is the most general operator in a symmetric traceless representation. If it's a mixed representation of OD, then it is not the most general one. Then I lose information. If you have a tensor, which is a tensor with two indices, mu nu, But imagine it is an antisymmetric tensor. If I contract it with two n's, of course I get 0 because mu and nu is symmetric. I contracted, I got 0. So of course I lost information.
I mean, at least it is.
But if it is totally symmetric and traceless, I lose no information by contracting it with a null.
At least it is in integer speed.
Oh yeah, definitely. Definitely. I'm considering here integers. Okay? And actually, I mean, this is already, we are already reaching kind of the boundary of what people know, because it's non-trivial, for example. It is non-trivial that when you have operators with spin, that there is still just up to a number, sorry, here I should write a structure constant again, C, up to a structure constant, and up to some dimensions, that this is totally fixed by symmetry. And for example, if you ask, what is the correlation function of three operators with spin L1, L2, and L3? It is no longer fixed by symmetry. Now there are different structures, different tensor structures you could write, and you can learn more about it in a paper from 2 years ago, 11073554. So if you want to learn more about operators with spin and more general cases, you can look here. For what we are going to do, this is the only thing we will need to know. So if you accept this for granted that operators take this form, and you don't even need to accept it because we are going to compute and check. But this is all we need to know to go on with our discussion. Okay? That conformal symmetry, if we work a little bit harder, also fixes the values of correlators involving two operators with spin or one operator with spin and two scalars. And I want to emphasize that conformal symmetry here is already playing a big role. Because, for example, if you only have with only scale invariance, for example, the only thing you could say about the correlation function of 3 points is that it would be a sum of infinitely many terms such that a plus b plus c is delta 1 plus delta 2 plus delta 3, 1 over x minus y to the a, x minus z to the b, y minus z to the c. Okay, where x, y, and z, you can guess what they are. Right? X1, x2, and x3. I don't want to rewrite. Okay? So you see that instead, with, of course, what's important is with infinitely many constants, C, A, B, C. Okay? So this is in stark contrast with the previous case where we say it is just a single number versus infinitely many. So if you have conformal symmetry, that is, if you have this inversion symmetry, this local scale invariance, it really is very powerful. You go from having infinitely many functions to fix, infinitely many constants to fix, to having one constant to fix. Okay? What about when you go to 4 points? Well, for 4 points, let's take 4 operators, O1 up to O4, where all the dimensions are the same for simplicity. Then what you know is the following, is that the result you can write you can take out some dependence on the positions, but then multiplying some explicit factor that you take out, there can be an arbitrary function f of u and v, where u and v are so-called conformal cross ratios. So these are combinations of coordinates that you can form only starting with 4 points that are invariant under conformal transformations. And conventionally, we define u to be equal to x1 minus x2 square, x3 minus x4 square, over x1 minus x3 square, x2 minus x4 square, I think, yeah. And v is defined as x1 minus x4 square, x3 minus x2 squared over the same denominator. And these combinations are invariant under conformal transformation. So there's nothing conformal symmetry can tell you at this moment about this function of u and v. And the easiest way to see that they are invariant under conformal transformation is, again, to note that they are invariant under inversion. Because under inversion, each distance, x1 minus x2, picks a factor of x1 squared and x2 squared. But that factor there, then downstairs you have x1 squared, x3 squared, x2 squared, x4 squared. So all these factors cancel out, and you get that this result is invariant under inversion trivially, right? So then it's invariant under all conformal transformations, obviously. So you cannot, so after you take out some explicit dependence that just makes sure that your object has the right scaling properties, this function here is, if you want, the juicy part of the correlator. This is really the interesting part. Right? So this is really the juicy part. Okay? And sometimes it's convenient to think about what are these cross ratios. If you have 1, 2, 3, 4, this is the distance 1, 2 times the distance 3, 4 divided by the distance 1, 3 and the distance 2, 4, whereas this one is the distance 1, 4 times the distance 3, 2 divided by this distance here. Kind of a nice graphical representation. Okay? So, very good. Any question so far? So all this was already in the first week, more or less, right? Maybe a little bit worded a little bit differently, but everything I said you saw in the first week. All the formulas were written before in a way or another, right? Okay, I think probably what I'm about to write actually also, but let's see. So let's now discuss what's called the operator product expansion, and at the same time we can discuss the state operator mapping. So these are very important concepts in quantum field theory and in conformal field theory in particular. So it's really quite crucial. And it's related to this map from the plane to the cylinder that we are discussing there. So we want to discuss operator product expansion and state operator correspondence. Okay. So the basic idea is that if we have two operators and we see them from very far away, they look like one operator. If you have 2 points and you look from very far away, it looks like 1 point. So the basic, what we want to do is the following. We want to take a sphere and consider 2 operators at 2 points inside that sphere. One, say, at the origin and one at some point x. Okay? These points are inside the sphere. So this, by this picture, we mean that we have an operator O1 at the origin and the operator O2 at some position x. And now I'm going to write something that maybe is obvious or maybe needs some motivation. So let me write it, and then you should tell me whether you think it's trivial or needs some motivation. These operators, seen from far away, they look just like one effective operator at the origin with some coefficient ci that could depend on x. And we sum here over all operators I. Okay? It's a little bit like if you have 2 charges and you look from far away, it looks like just a charge that is the sum of 2 plus some dipole moment plus some quadrupole moment and so on. And you are just looking from far away and replacing the 2 operators by some effective operator plus some small correction plus something else. And you are taking into, and this is what you expect. If you look from very far away, how could you know if inside there is 1 operator, 2 operators, 3 operators? You don't know. You just replace by 1 effective operator plus a correction plus another correction and so on. Right? So this is the physics. Now let's see how we can, if we were explaining this to a mathematician, how would we do? It would be tough. So we would say that at this sphere, we have some state capital psi, some functional capital psi, right? We are doing the path integral, and here we have some functional of my field, some state that defines the state psi. Is this good? How do I think of this state psi? For example, one convenient way of thinking of the state psi that makes it convenient because we have this notion of time propagation instead of radial propagation, but even though it's the same, is to think that this state is here defined some state psi to the future of these insertions of my two operators. One of them here and the other one at tau equal minus infinity, which was the origin. So I have these two operators, and now I have some state here, some state psi at some point in my cylinder here, right? Now I could imagine undoing the path integral. I start with some state psi, and I do the path integral with this boundary condition being this functional, and I undo the path integral to the past. So I start with my state psi, and now I go back undoing the path integral. So what is the wave function here?
What do you mean by the state? Do you mean like the boundary just level of the field?
No, I mean, what is the wave function in quantum field theory? You say that I compute the path integral, where at some given surface, I impose the boundary condition that the wave function approaches some field configuration, right? The path integral depends on that field configuration. This is the wave function. It's some state psi that depends on the value that I assign for the field at this d-dimensional sphere. So it's a functional. So in this sphere, I say, let me see what's the probability of getting a constant field in this sphere. And I do the path integral with the boundary condition that the field is constant. What's the probability of getting a field that has a bunch of bumps, like a star? I impose that boundary condition and I do the path integral. This is the wave function. For any field that I put on the sphere, I get an amplitude of probability for getting that field.
You mean surface of the sphere?
Yeah, on the surface of the sphere. Sorry, surface. Yeah. Sorry, yeah, good. So you undo the path integral. And this state here, as you undo it, you go back, should correspond to putting some state at the very past. And this state at the past will be some sum of some linear combination of the states in my Hilbert space of my theory. And then I'm translating back, I'm just writing back that if I have a linear combination of states, it's a linear combination of operators. Okay? And I complete this circle of ideas. Which we can also write in the following way, which is a bit more convenient. Instead of summing over all operators, we say that we sum only over the primaries. Okay? And then we sum over the primaries and we write ck of x times ok of x. This is a primary. And then there is a descendant, and I will put it here, ck mu of x times the derivative of this primary. This is a descendant. Plus c mu nu of x times d mu d nu of this primary. Plus, So I sum over primaries, and for each primary, I sum over its descendant. So I organize my sum over all states of my theory by separating it into a sum over primaries, and then for each primary, all the descendants that I trivially obtain by acting with a momento on the states, I treat at the same time. Good. So this is the essence of the title of what I said. So what we have done here is, without mentioning it explicitly, we were using back and forth this map between states and operators, and we defined here what is called the operator product expansion, which is a very important concept. Even simple as it is, it's a very important concept. It's an algebra, if you want, that tells you that you take two operators, O1 and O2, and you get a third operator, OI. So you can think of it as an algebra. It's kind of an infinite algebra, but it's an algebra. And it's a very powerful ingredient of an OP. And as with any algebra, you might wonder, are there constraints on this algebra? What happens when I start taking many operators and fusing them in different orders? Can I learn something about conformal field theories? And will this pose an important constraint of the theory? And the answer is yes, indeed, as we will see at some point. Okay? Good. So now let's see what can we say about the operator product expansion. What can we say about this coefficient? Do we know these coefficients? Can we predict them? And the answer is almost. We can almost predict all of these coefficients. Let's see how. It's not complicated. It's actually very straightforward. Let's consider for that a 3-point correlation function. Consider a correlation function, O1 at x1. I'm not sure if I want to put some operator at the origin. Of course I can, but I'm not sure if it's useful. Yeah, according to what I wrote here, it's useful. So let's put the first operator in the origin, O1 at 0, O2 at x, O3 at y. Okay? And now let's massage this equation from two different points of view. On the one hand, we are going to use the fact that we know the result, we know what this is. Right? This was predicted by symmetry. On the other hand, we are going to use the fact that we can replace these two operators by their OP. And then we are going to see, comparing both points of view, what will this tell us about the OP structure constants. Okay? So let's put here what we are going to use. Oh, it's not here anymore. What a pity. So on the one hand, we know the result for this 3-point function. And let me write it a little bit, reorganizing a little bit the terms, but you will soon understand that it's clear. I don't want 3 here. I want to put k. Sorry. K because it was the k there. So here we have the structure constant, C1 to k, this important number. And then let me write, and it will become clear, 1 over x to the power delta 1 plus delta 2 minus delta k. This is x minus 0, but 0 is 0, so you don't see. Then there is y minus 0, that you also don't see the 0. You just see y to the power 2 delta k. Where are the other deltas? I'm considering now operators with the same delta. So let delta 1 be equal to delta 2 be equal to delta. No, actually not. I'm not considering this. But it's just that we can rewrite it in this way, because there is an extra term here. And this extra term is 1 minus 2x dot y over y square plus x square over y square, everything to the power delta 2 minus delta 1 plus delta k over 2. Okay? So I'm going to spare you the details of going through the algebra. All I did there was replace x minus y square by x square minus 2xy plus y square, and then put some powers of y square inside some brackets, do some massaging of the result that you would trivially write. Is it clear? So this is just conformal symmetry. And now you can expand this at small x. And what do you get? You get that this is equal to, let's write here, this is equal to C1 to k, absolute value of x to this power, absolute value of y to that power, and then let's just expand the first term. 1 minus what? Minus the factor of 2 cancels the factor of 2. Help me out. Tell me if I'm doing it right. Delta 2 minus delta 1 plus delta k. The 2 just cancels. X dot y over y squared plus dot dot dot. Okay? So this is what we get on the one hand. We could expand further a little bit more. Okay? So this is 1. On the other hand, from a different point of view, I can replace this O1 and O2 by their OP. Right? And when I do it, what do I get? I get a sum over all primaries. Let me call it K prime, not to confuse with this K here. Okay? Of what? Of sum over k prime, and then sum from n equals 0. Now, I actually will write it explicitly, sorry. Let me see, how do I want to do it? I want to do it like that. Times c k prime 0 and x, c k prime of x times the operator O k prime at 0, O k at y. Right? That's the first term. And then the second term plus c mu k prime of x, derivative with d mu, where this, okay, well, let me write and it will become clear, of OK at 0, OK of y, whereby this derivative, I mean the derivative that is respect to this position that I'm putting to 0. So I should put to x, then take the derivative, then put to 0, or if you want, take derivative with respect to this guy, but then put a minus sign. Okay? It's clear? Plus c mu nu, d nu of the correlator, and so on. Do you agree? But now, each of these correlators between k prime and k is 0 unless k is equal to k prime, unless you have the same primary. So this thing here is delta k prime, they must be equal, times 1 over x minus y, or no, sorry, just y to the power 2 delta k. Do you agree? And this thing here, the full thing here, will be c mu k y mu over y to the 2 delta k times y squared after taking the derivative. Take the derivative, you get an extra power of y. Is it okay? So y dot c from the derivative, and downstairs there is an extra y squared after taking the derivative, and so on and so forth. And now you just compare both. And when you compare both, you realize that beautifully, this term here, this one, is to be compared to the first term here. This term here, that has this extra power of y and y squared, ought to be compared with this term here. Ought to be compared with this term here. And so on and so forth. So let me write what the result is, and it will be clear if you look at the expression that this is indeed what follows from there. What we are seeing is, so let's write what we are learning about this. We are learning that the first term in the OPE is nothing but the same constant that appears in the 3-point function. So here is what we are learning. We are learning that ck of x is equal to the structure constant c1 to k, this number, times x to some power. What power? Let's see. X to the power delta k minus delta 1 minus delta 2. And that's it. And then we learn that c mu k of x is equal to the same thing, c1 to k, x to the power delta k minus delta 1 minus delta 2. I did a mistake here. When I take a derivative of y to some power, you get delta, right? You take the derivative of y to the delta. Of course, there is some delta k here that I forgot. You agree? There is some delta k here with a factor of 2. There was y to the power 2 delta k. I took a derivative, I got 2 delta k. So now once we solve, we get downstairs 2 delta k here. And upstairs we get delta 1 minus delta 2 minus delta k times x mu. Because you need x dot y, so this is what Cx of. And you could go on, and you would find that C mu nu of xk is equal to, again, C1 to k times some tensor, B mu nu x of k. But the point is that this tensor is totally fixed by conformal symmetry. This is where the dynamics sit. The rest is just kinematics, right? So this number here tells you, I mean, it's very intuitive, right? So you take your two operators, and you say, my two operators fuse into a third operator. With what strength do they fuse? Well, it's very easy. I use the operator OK. I put the operator OK here. This singles out OK in this fusion, and we'll measure with what strength these operators are fusing to give OK. You agree? So that's natural, that each of them is proportional to the structure constant. That's perfectly natural. So by just putting OK and two operators, you fuse, and you measure the fusion of these two operators with OK, you measure the 3-point function. But then what we are saying is that, OK, but the probability of producing a primary or a descendant or a double descendant or a triple descendant and so on, they are not free, but rather, once you know the primary, the other ones are proportional to the primary, and all these tensors are known. You could just now repeat on, continue on this exercise and find out what this B mu nu is, what the B mu nu rho is, and so on with more and more indices, and you could a priori fix all these tensors and fix completely this structure. And what you find out is that the most general case, you get some structure constant, C1 to K, times a tensor that is totally fixed by symmetry.
What about primaries which are not scalars?
Good, but yeah. So that's one question. What about primaries that are not scalars? I want more questions. It's important to have questions here. More questions.
I have a question.
Yes.
Yes, I understand. You understand the operator product expansion in terms of correlators, okay? So, like for example, if you have, for example, product of two operators, okay, and you write it as a sum of operators, okay, and you demonstrate it on the example, for example, of writing 3-point function in terms of 2-point functions, okay?
Roughly, yes.
Yeah, and so my question is, for example, okay, suppose that I want to write, for example, in the same way, for example, 4-point function in terms of 3-point functions, okay?
Yes. You can do it.
Yeah, so the question is operator product expansion the same in this case?
It is, yeah. Because it's really a property of fusing two operators. It is an identity that holds inside any correlation function with whatever you put. It's really a property of, it has nothing to do. In other words, you start with this state here, and you evolve it, and this state is an outcome of putting these two operators here. It has nothing to do with whether you have an extra operator here, or an extra one here, or an extra one here. It will be totally insensitive. You are doing the path integral up to here. What do you know if there are more operators here? So for a 4-point function, you would have two operators here, two operators here. And what you are saying is that these two operators can be replaced by a sum of states. That's fine. It has nothing to do with whether afterwards I will have two operators or three or 1 gazillion. It is just a property that if I have two operators here, I can undo the path integral and write them as a sum of operators. And then on the top, I can have a third one, or a 4 or 2 more, or I can have 1 million more.
And so does it mean that the statement is true only for conformal series?
It is true beyond conformal theories, but the problem is that beyond conformal theories, you don't have an organizational principle that tells you what these C's are. So it becomes very useless because these C's will depend on energy scales, and it will be
yeah, sure. But I mean, the question at least is it the same? For example, if we write this O1 and O2 inside 3-point function, or we write it inside, for example, 4-point function.
This is the same, yeah, in a CFT. Yeah. You're asking outside the CFT?
Yeah.
Outside the CFT, I'm not positive. I would have to think about it. I'm not totally sure about rates of convergences and how things work for operator product expansions outside CFTs. It's still possible to do. It's again the same physical idea. You just have two operators. You see from far away, it looks like a sum of operators. But now these structure constants do depend more deeply on the scale, and it's not true that you can isolate them. So the short answer is that probably actually no. Inside a correlation function, if it is not a CFT, because the theory will want to know about all the scales, I think it might be tricky if you have more operators. In a CFT, it's definitely correct. You just have two operators, again, the argument again. You have two operators here, and they generate some state psi here. They don't care if there is more operators here, and what happens. This is definitely true. Let me now answer the question about spin. What would happen if you would have spin? Well, if you have an operator with spin here, right? Let's put some spin here. The right-hand side is still no. Now you have an extra tensor here. You agree? But it is still no. So the answer is that you can repeat exactly the same thing. But now you are expanding something different, so these things will change, and therefore the structure constants will change. So if your operator has spin, even the first term you would write a bit differently. Now you would put immediately, for example, two indices here, mu nu, and here mu nu, even though it was a scalar to start with. So your starting point would be two indices right away for a spin 2, for example. And then 3 indices for a descendant, 4 indices for a descendant, and so on. But then you would take these constants, plug them here, write this line. The first line you also know, so you can also find all the structure constants if you have one operator with spin and two scalars.
I have a question about this picture. So if I evolve psi backward,
yes.
I will get some state, and I can write that in some basis. But how do we know that there's a one-to-one correspondence between the basis vectors of Hilbert space and the space of operators?
That's by the definition of an operator or of a state. So whatever the state is, so if I have a state down here at some distance epsilon away from minus infinity, whatever that means that by undoing, what I'm doing is that I have my origin and I have a very, very small sphere generated by this state. So for any state here, I evolve it by some distance epsilon and I generate some very small wave function. Similar for any small wave function, I can undo and get an operator. So whatever I get, I can say that take any operator, evolve it, get a wave function, squeeze it back at a state, back and forth. And by continuity, it's unique. Good. Okay, so now what are we going to do? Okay, so now that our friend left, we are going to answer his question about 4-point functions. Okay, very appropriate. Maybe we'll wait a little bit for him to come back and while you ask some more questions. More questions? This is something important. So, I mean, it's a very crucial notion in conformal field theory that you have this operator product expansion and that it is to a great extent fixed by conformal symmetry. And now we are going to start seeing how can we use this power to start learning about more interesting observables like the 4-point function and this f of u and v. Okay? So what we want to do now is show that in a CFT, there is a notion of something called the CFT data. What is the CFT data? It's the set of all dimensions and 3-point functions. And what I want now to show you is that if you know all the 3-point functions and all the 2-point functions, so all the dimensions and all the structure constants, you can construct any n-point correlation function. So giving a CFT is synonym to giving me a list of all dimensions and all structure constants. So let's go. So I'm doing much more than I thought I would. Either I'm doing way too fast or okay, or not.
I agree.
Yeah. Am I going too fast? So if I'm going too fast, please stop me. But okay. I will have to prepare tomorrow's lecture. I thought this would be enough for today's. Okay. Let's now consider a 4-point correlation function, and let's speak very slowly. Okay, so we have a 4-point correlation function of 4 operators, O1, O2, there is O3 missing here, and up to O4. And we want to consider this correlation function. So what can you do? You can now consider the OPE of these 2 operators. So you have your 4-point function, and you are considering a sphere that surrounds 2 operators, and asking yourself what happens when I fuse these 2 operators. And what do you get? let me write right away. You get the following. You can replace them by a sum of k, where these are the primaries. Okay? With, and let's put spin as someone else. Let's put spin here with some dimension delta and some spin L. And then let me write the following equation. Let me take out C1, 2k. It's obvious why I want to take this out, because I get it from the product of these two. You agree? But let me also take out C, K3, 4, for reasons that will become clear. And now let me write an equation. What appears here is what? You now sum over all descendants from 0 to infinity, b mu1 up to mu n, that depends on this x2 minus x1 for operator k, times the correlation function O. So we are now answering your question about 4-point functions, okay? So we are starting with a 4-point function and replacing two operators, putting them inside a sphere and replacing them by their OP. Okay? So what do you get? You replace these operators by, you see them from far away, there is a sum over primaries, and I decided to take out these two factors, times what? Times the correlation function, okay. Sorry. Times this b's, times derivative with respect to x1 mu, derivative with respect to x1 mu L, there are n derivatives, times the correlation function of the operator OK with some spin delta, some dimension delta and spin S, O3 and O4, okay, divided, because I multiply, by the structure constant CK34. Do you agree with this equation? Yes? So now, let's see that, note that what we wrote here is totally fixed by symmetry inside this bracket. So these guys, right? These guys are fixed by conformal symmetry, right? After you take out the structure constant C, this B were totally fixed by conformal symmetry, right? These were just, right? This is B without indices, B with one index, B with two indices, and so on. What about the 3-point function? The 3-point function is fixed to conformal symmetry up to a number, but we divide by that number, right? So this stuff here, divided as it is, it's also totally fixed by conformal symmetry. In fact, this is nothing but, did I erase? I did. Wow. This is nothing but we had written here for some spin. I wrote some expression for the correlator with spin. This is exactly what it is once you divide by that constant. Okay? So what do we have? We have that you can always write a correlation function as a sum over k, C1, 2k, CK3, 4, times a function, let's write it capital F. It's a complicated function, but it's totally fixed by symmetry. It's like a Bessel function, or some cosine, or some sine. It's a complicated function. You might have to suffer a lot to compute it once. But you compute it once, you save it, and it's the same for all CFTs. It has nothing to do with the dynamics of your theory. It's just the analog of useful functions that we have for summing over expansions, like plane waves, spherical harmonics, and so on. It's just a function, whatever it is. And this is what is called, that depends on delta and del, this is what is called a conformal block. Okay? So this is the famous picture that you probably have seen before, that we can write any 4-point correlation function as a sum over what flows in the OP of two of the operators. This is this famous cartoon that you have seen for sure, where you write that a 4-point correlation function, O1, up to 04 can be written as a sum over a product of you sum over what flows, and you have the structure constant. And this cartoon stands for this precise formula. Okay? So the point is that we have this notion of this CFT data. A CFT data is a set of dimensions and structure constants from which, by successive application of the OPE, we can compute any endpoint correlation function. And here is an example for 4-point correlation functions. Okay? Is it clear? So we could write, I can write to you down what this, how this conformal block looks like. You might be curious. Is it like a spherical harmonics? Is it like a plane wave? And I will write it soon. But let me first point out, let's go on with this abstract notation discussion. And we could point out that we could have drawn another sphere. We could have taken another 2 points, and we could have done the OPE in another channel. Instead of summing over what flows from inside that sphere to outside this sphere, we could have drawn another sphere, like this green sphere, that encircles these 2 points. It has some overlap with the other sphere, that's fine. And we could sum over what flows from inside this sphere to another sphere. And this would lead to another representation that will tell you that this is equal to a sum where I fuse in some different channel. Right? And this leads, if you want, and this is a very powerful constraint. This is nothing but associativity of the OPE algebra. It tells you that you can fuse in different orders and get the same result. And this is a very powerful relation, so powerful that we can replace our definition of a CFT by an alternative definition, which is as good as this one if you want. And the definition is the following. So let's write a new definition, definition 2 of a CFT. Totally non-perturbative definition. A CFT is a set Cijk. So it's a set of a table, a big table of numbers, all delta i's and all ci's jk, which obey the so-called bootstrap equations that tell you that it's a consistent algebra. So I can define my CFT. I can tell you, my definition is that the 3-point functions are given by these numbers and the operators are given by these numbers. And why not? Why can't I define it like this? I can. I just postulate. I will postulate that 2-point functions are given with these critical exponents. And 3-point functions are given by this structure constant here. A priori, I can do whatever I want. However, the only point is that I must do something that is consistent. And I must do something that obeys the analog of Jacobi relations and so on, which is the bootstrap equations. So if I'm powerful enough, and this is very hard, to give you a set of numbers, delta I and Cijk, that obey the bootstrap equations, this is as good as a definition of a CFT as it gets. So this is a definition that is absolutely equivalent to the previous one, and it is really an equation based on this conformal bootstrap approach. Sorry? No. Yeah, no. This is a definition of the part, yeah. If you want to ask now that in your CFT you also can compute non-local operators and so on, you would have to think a little bit on how to incorporate it here. Okay? This gives you a definition of what are the properties that correlation function of local operators must satisfy. Both this definition and this definition. If I want a theory which has some Lagrangian and where I have Wilson lines, Tooft lines, and whatnot, then I must work out new rules that take those into account, both here or here. And I'm not doing this. Okay? So if your theory is, say, a gauge theory, indeed, you have Wilson lines, surface operators, and so on. So here we are focusing on the simple set of observables, local correlation functions.
So this is a nice graphical operator. What does it mean mathematically?
No. It means exactly this. I sum over all operators of my theory, structure constant, conformal block, which is a known function, is equal to the same thing when now I replace x1, x2 by x1, x3, and I relabel the points. So it's really this equation equal to the same thing if you were to repeat the exercise in a different channel. So it's a very, very precise equation. Is it clear for everyone? It's very precise. So let's write down the final outcome of this discussion in terms of the interesting variables, which are not x1 up to x4, but rather these conformal cross ratios. So I can write this conformal block. I can take out the part that is the trivial space dependence times a function of z and z bar. So the conclusion, let's summarize it here to start tomorrow from this point, is the following, or maybe here. This is good. This is very good, actually. The conclusion is the following. Take this definition of the conformal block, of the conformal cross ratio. And actually, it is also convenient to introduce a new letter, z and z bar, which is an equivalent definition of this v and u. I can tell you about the geometrical meaning of this z and z bar, but this is just a redefinition of v and u. Just convenient to use this letter z and z bar. Then, with these definitions here, a correlation function of 4 operators, O1 up to O4, is equal with all with the same dimension delta now, for simplicity, is equal to 1 over x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta. So this is what is written there at the very end, right? Times a reduced amplitude f, that is function of u and v, or in other words, z and z bar, it's the same. And this function here, what we know is that this function, you can write it as a sum over all primaries with dimension delta and spin L, structure constant 1, 2 into an operator delta and L, structure constant of operator delta and L into operators 3, 4, times this function that is totally fixed by symmetry f, that depends on delta and L, of z and z bar. This is the conformal block after you take out this trivial dependence. Where, and here we are in 4 dimensions, where this conformal block that depends on delta and L is equal to, now you see why these variables are useful, z bar over z minus z bar. So if I were to write this with u and v, it will be a bit complicated, some square roots, but that's the only thing. And then there is some convenient function h of delta plus L over 2 of z times a function h of delta minus L minus 2 over 2 of z bar, minus the same thing with z replaced by z bar. We are almost there, where h lambda of z is z to the lambda times the hypergeometric function f to 1 lambda lambda to lambda z. Okay? Is it okay? Now, this might seem very complicated. I want to point out 2 things, that conceptually this function is complicated, f delta of L. Remember, this function is nothing but this function that you can totally fix by symmetry.
So just is f multiplied by the fraction here, in the full expression for the full
here?
Yeah, no, above.
Yes, it is. There is a square bracket here. So it's this fraction times f, where f meets this expansion here. Okay? So what I want to point out is that this function here is very complicated, but we can compute it, right? You just find out all the mu nu, you substitute the expression for 3-point function, you sum the first 100 terms, you start seeing some pattern, you Taylor expand this function to the first 100 terms, you see it's the same, then you compute 100 more, and you get convinced that this is equal to this. Now, it might look a bit intimidating. How would I ever guess that by doing this carefully and so on, that this would resum to this nice expression with hypergeometrics? Right? It might look a bit tricky. So next time, I'm going to show you an alternative derivation of this conformal block that is not the brute force derivation, where we understand better what is the origin of these hypergeometric functions and so on. But I do want to point out that actually this brute force way was the way that Dolan and Osborne in 2004 first did it. They really analyzed this function, saw some patterns, and they managed to guess that this mess was nothing but this nice hypergeometric here. But a priori, the precise form of this is not important. What's important is that this is some known function that is totally fixed by symmetry. It could be a function in Mathematica, conformal block of delta L ZZ bar. And you click Shift Enter and get a function. It has all the rights to be a function in Mathematica, like Bessel function, spherical harmonics, and so on. It just turns out to be this function, written in terms of a product of two hypergeometric functions. And as you see here very explicitly, now if you want to compute a correlation function of 4 points, all you have to do is sum over all structure constants of your theory that you need to know, summing over all the dimensions of your theory that you also need to know. So if you know the full spectrum and the full 3-point functions, this is totally fixed. All you have to do is perform this sum, and you get the 4-point function in your conformal field theory. So this is how you can very, very explicitly write down a 4-point function in terms of the most fundamental building blocks. Is there something else I want to say? If people don't ask now. Yeah, good.
So this is the explicit function in 4 dimensions?
Yes.
Is it known in any dimension?
It is known in any even dimension, and in odd dimensions it's not known. Even in 3, it's not known. Even though it is still taught, this argument here goes through in any dimension, and you can write a series expansion. But no one managed to understand what is the resummation in 3 dimensions.
It is known to like some order and something in all dimensions.
Sorry?
Is it partially known?
It's partially known. There are many things that are known, yeah. There are many, many things that are known. Let me postpone the answer to that question for tomorrow. Tomorrow we are going to analyze conformal blocks in more detail, understand a little bit better, 1 minute. And it will hopefully be clear what is known. Okay? So please, so as I did not know if this was going to be important for tomorrow or after tomorrow or something, we are going to start with that tomorrow. So do think about that. You don't need to do in all details. You don't need to show that it commutes with all generators. If you check that it commutes with 1, I'm happy already. And think about the second point. What is the action of that Casimir operator on a scalar primary? Okay? So that is enough. See you tomorrow.